You are welcome again in our organic class. So we start with the second lecture from the polycyclic aromatic hydrocarbons. We stopped here in the fused ring benzonide, and we will continue with our subject for this title. So fused ring benzenoids means that the ring share two adjacent carbon atom and common bond. So if you look here to this structure, okay, you will be see two cycle bond together, and there is two adjacent carbon related with the two cycle, sharing between the two cycle, and common bond, one bond here. Here, in this case, we said these two cycle, they are fused together. Okay, it is different from the biphenyl compound. So this compound in organic chemistry has special electronic structure. Also, there is resonance stability. It's different from the isolate cycles. The first example for this compound is the naphthalene. Naphthalene is an organic compound with molecular formula C10H8. It is simplest polycyclic aromatic hydrocarbon, the smaller one from this family. Consists from two benzene rings fused together. This is the naphthalene, two cycle of the benzene ring. And when we put number, we start from this carbon: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This 9 and this it will be 10. The carbon atoms sharing between the two cycle, it will be take the last numbers. So this it will be 1 alpha, 2 beta, 3 also beta, and 4 alpha, this alpha, this alpha position, and beta position. That meaning we have 4 alpha position and 4 beta position here. Another example here. Look to this naphthalene substituted with hydroxyl group. We said 1 naphthol or alpha naphthol. Both of them is right. Okay, 1. This is the position number 1. Also refer to this position by alpha naphthol. 2 naphthol or beta naphthol. Okay, beta naphthol. Look here. 1, 3, 4, 8. That meaning 1, 8 dibromo naphthalene. Naphthalene compound. Okay, naphthalene compound. Here. Naphthalene 2,7 disulfonic acid. Here is acidic. This compound is acid compound. So naphthalene 2,7 disulfonic acid. Okay, disulfonic acid. This 2, we have 2 nitronaphthalene or beta nitronaphthalene. And like that. Alpha naphtholamine, alpha naphthalene sulfonic acid. This alpha naphthalene sulfonic acid. This about how we can name it, the compound that are derived from the naphthalene. So the aromaticity, because it's contained two fused ring with decollized pi electron. طبعا we have mistake here. This pi electron, okay, you have to delete this sample for the dollars and slash. It is just pi electron system. It is highly highly stable compound. So this is the first resonance structure, this the second resonance structure, this the third resonance structure, like that. Okay, this like this. So we have three resonance structure here. This bond it will be come to here, and this bond to come to here, and this bond to come to here, like that, to give you this the second structure. Reaction of naphthalene. The first reaction of naphthalene is the oxidation. Oxidation. We said we know oxidation increase the oxygen atom or decrease the hydrogen atom. So here by using, we have two type of oxidation here by different طبعا by different reagents. So again, the process it will be under high temperature. The high heat and catalyst cause the complete oxidative breakdown of one of the benzene ring. The ring is broken open, and two carbon atoms are, it will be lost from the structure, usually released as carbon dioxide. So if we go again to this structure here, to this reaction, this both of these two carbon here, this bond it will be breakdown, and this both of the carbons it will be lost as carbon dioxide, CO2, from the structure, and to give you finally phthalic anhydride. So we don't take the mechanism for this reaction. It is just a special mechanism. Without mechanism, just you have to memorize this reaction under hard condition. It will be give you completely oxidation to go to the cyclic anhydride. Cyclic anhydride. So what the note here, because the naphthalene is sensitive to oxidation, you cannot make naphthoic acid via oxidation of side chain. Okay, oxidation of the side chain. So if we go here, you want to by just like KMnO4 to make oxidation just for this R group without oxidation to the naphthalene group. So the reaction cannot be happened. Yani this it will be not convert to the COOH to the carboxylic acid group, but the naphthalene it will be enter before the R group to the oxidation reaction to give you this compound. Also, this ketones compound, if you want carboxylic acid group substituted on the naphthalene, you have to use this type of reaction from the acyl naphthalene substituted the acyl group, this acyl group, this ketone group, ketone compound. So this functional group as methylene ketone can be oxidized to the COOH, to the carboxylic acid, by using NaOI. And this is the reagent used to this process. So synthesis of the naphthalic acid, this is the naphthalene ring with carboxylic acid group. It will be provide successful workaround by this reaction. So again, as explanation here, we said direct oxidation doesn't work. This doesn't work, but it will be used the haloform reaction, the second one reaction by using NaOI. This reagent is the haloform reaction. The haloform reaction is highly specific to the methylene ketone. We say to the methylene ketone, it is selectively cleaves the carbon-carbon bond on the acyl group, okay, transferring into carboxylic acid group. It will be go to the COH and leave the sensitive naphthalene ring perfectly intact. Okay, it will be remain as naphthalene. So the second reaction for this naphthalene compound is the reduction. So if we look here, reduction can be happened by using sodium in alcohols to give us 1,4-dihydronaphthalene, or it will be, this is not full reduction. Okay, it is not full reduction. This is mild reduction, moderate reduction here. It will be converted to the tetrahydronaphthalene, tetraline, we said tetraline, or completely reduction. Both the ring, it will be saturated with the hydrogen atoms. So decaline, it will be give you this two cyclohexane ring fused together, this compound called decaline. As explanation for these three reactions above, partial and complete reduction of naphthalene aromatic hydrocarbon, each pathway demonstrate how varying reaction condition it will be work, reagent and temperature. So the reagent temperature, it is very important factors can be can be work in the reaction. So the partial reduction here, as I said, for partial reduction, it will be give you 1,4-dihydronaphthalene reagent the sodium and ethanol. طبعا the ethanol here, the solvent, it will be source also for the hydrogen atom. Results here, only one ring, it will be partially reduced because 1,4 addition is completely favored in this system. Okay, we get just 1,4 dihydronaphthalene. The other ring cannot be affected by this process. It will be remain fully aromatic يعني system. Further reduction for the tetraline, also it will be using by sodium and isopentyl alcohol. This is the isopentyl alcohol. Look here, the temperature is higher than from the first reaction, okay, at higher temperature. So by increasing that temperature, using higher boiling point alcohol like isopentyl alcohol. طبعا at high temperature we cannot use ethanol because the ethanol, the boiling point of the ethanol, you know, it will be 78, and the temperature cannot be increased above to the 78 because the ethanol. But if we used another solvent, another alcohol, but that has higher boiling point, so in this case we can increase the temperature for reaction, and it will be stopped to the 132, the boiling point for this alcohol that used in this process. So the product, as I said to you, it will be tetraline. This is a very stable solvent because the remaining benzene ring is resistant to further reduction under this condition. Also, the reduction can be happened full reduction for both of the cycle. We put excess hydrogen gas and platinum as catalyst under heat and the pressure. Look here that what we use here, heating and the pressure, harsh, yani very hard condition here to be applied on this reaction. For this reason, it will be give you fully reduction for both of the naphthalene cycle. Another type for the reaction of naphthalene, and this is not new for you, is the electrophilic aromatic substitution, again for the aromatic compound, as we know in the benzene ring. So this example we have naphthalene, go to the nitration, so it will be give you nitro group at alpha position. Look, the nitration here is different from naphthalene, from the benzene. So the reagent here is nitric acid, usually used in combination with sulfuric acid, HNO3 add H2SO4 to generate the nitronium ion. This it will be electrophile. And the benzene, or sorry, the aromatic one of the aromatic cycle, this or this, it will be attack this the electrophile. The product here, it will be 1-nitronaphthalene, alpha nitronaphthalene, 1-nitronaphthalene at alpha position. So the question here, he said, why the alpha 1 position? Why NO2 enter to the alpha position, not to the beta position? So again, why the electrophile enter to the alpha position, not to the beta position? Of course, this related with the stability of the intermediate compounds during reaction. It is related with the mechanism. So if we go to the mechanism, how the benzene ring of naphthalene will be attack the electrophile and give you carbocation. What is the difference between the attack when they happened in the alpha position or when they happened in the beta position here? So upon examination of resonance structure below, we can see that among 4 structures, 2 structures shown stable form with perceived aromatic stick. More explanation here. If we look at in this structure, so the one of cycle of the naphthalene, one the aromatic cycle of the naphthalene, it will be attack the electrophile at alpha position, this alpha position, and the carbocation, it will become positive charge, it will become to the beta position. So here, if you look to this resonance structure, this benzene ring that has aromatic properties, and here the aromatic system, it will be destroyed. Okay, so this pi bond, it will be make double bond, and positive charge to be converted to here, give you second resonance structure. This pi bond, it will be converted to here, the positive already, it will be here. If you look to the second resonance structure, this benzene ring has aromatic system. So this is second cycle without aromatic system. So third resonance structure, if you look to the both of the cycle, they are without resonance, without aromatic system. That meaning this cycle there is no aromatic system. Also this cycle there is no aromatic system. We said aromatic state destroyed. So the aromatic system destroyed here, also destroyed here. When this double bond when pi bond open to make double bond here, the positive it will become to here to give you the four resonance structure. Also both of the cycle here without aromatic system. So anyone is the more stable one here. Anyone is the more stable one here. This is more stable because one with aromatic system, one without aromatic system. This also stable, one with aromatic system, one without aromatic. This both of them, they are less stable than this two structure. Yani structure number 3, structure number 4, they are less stable from the structure number 1 and 2. Okay, so we have two resonance structure stable and two resonance structure not stable. If we go to the beta attack, this is the beta attack. When the electrophile, it will be come to the beta position. So we have carbocation here. This with aromatic system, the aromatic system destroyed here. If make second resonance structure without aromatic system, this without aromatic system, this without aromatic system. Third aromatic resonance structure, this is the third one, also without aromatic system. Fourth resonance structure, if this come to here and this come to here, the positive it will be come to here. So we have 1, 2, 3, 4 resonance structure. A 3 resonance structure, this and this and this, they are less stable. One of them is more stable than the other. Anyone is the best, in your opinion. Anyone is the best. 2 resonance structure stable, 2 not stable, or just 1 resonance structure stable with 3 not stable. Of course, this pathway is preferred. This is the preferred one. So the alpha position is active in the electrophilic aromatic substitution than is active than beta position. Okay, is active than beta position. So when the question again come to here, why the alpha position for the electrophilic aromatic substitution in naphthalene is more reactive than beta position, the answer it will be this the answer. This the answer. Okay. So when the aromatic state is perceived, yani not destroyed, the electrons are decollized to form stable carbocation. We have stable carbocation. So we can say that when incoming group attack alpha position, it generates more stable carbocation than beta position, more stable resonance structure. Also we have sulfonation. Sulfonation at low temperature is kinetically rules here. It will be happened in the alpha position, but at high temperature it will be happened at beta position. beta, it is this thermodynamic process. Okay, thermodynamic control it here. So the first one, in the top reaction, naphthalene react with the sulfuric acid at lower temperature. Here the lower temperature, 80, not room temperature, but at lower temperature. The major product is one naphthalene sulfonic acid. Also is the alpha isomers, where the SO3H group attack to the position right next to the ring junction. Okay. يعني here we have two isomers here. One of them when the SO3H come to here, the second when the SO3 come to here, or the SO3H come to here, or the SO3H come to here. But all of them, because we have four alpha position here carbons, this alpha carbon, alpha carbon, alpha carbon, alpha carbon. So all of them, they are same, and give you here one product, one isomer. So the explanation at lower temperature, the reactions is under kinetic control. This means the product that form fastest is the one that it will be predominate during kinetic control. Anyone it will be happened faster than the other. The electrophilic attack at the one position, alpha position, has lower activation energy, has lower here activation energy, has lower activation energy because the intermediate carbocation formed is more stable than the attack at two position. The same explanation, this explanation, the same explanation here and this here, the same here. Is more stable, that meaning more stable, that meaning has lower energy. So under low temperature, diamond kinetically control, it will be demononate, يعني it will be pre-demononate here. So at high temperature, in the bottom reaction, the same starting material are heated to the much higher temperature of 160 degrees. So the product here, the major product is 2 naphthalene sulfonic acid. The beta isomers, we say that also called the beta isomers, where the SO3H group attach one position farther away from the ring junction. Okay, farther away from the ring junction. يعني at beta position, it is far from the carbon here bridge between the two cycle. This position near from the carbon junction, but this position far from the carbon junction here. So the explanation here, at higher temperature, the reaction is under to the thermodynamic control. Sulfonation is reversible reaction. Okay, sulfonation here is a reversible reaction. So as explanation, what is the difference between kinetic product, kinetically control, or thermodynamic product, thermodynamic control? We said at higher temperature, the reaction is under thermodynamic control. Sulfonation is reversible reaction. Sulfonation process is reversible reaction. يعني when the sulfonation will be happened, can be go back again to the starting material. Okay, can be go back again to the starting material. The high heat provides enough energy. So at high temperature, when the high temperature it will be applied to this reaction, it will be give enough energy for the initially formed one naphthalene sulfonic acid, this one naphthalene sulfonic acid, to revert back to the starting material, and it will be go back again to the starting material. Okay, it will be go back to the starting material. and react again over time. The reaction will be happened and go back to the starting reaction will be happened and go back to the starting material again. The reaction reaches an equilibrium that strongly favor the most stable overall product. So when the beta sulfonation will be happened at high temperature, it will be not received, it will be not reversible again to the starting material. It will be not give you again starting material. So the thermodynamic product formation is slow. This reaction is slow, and it will be don't desulfonate, yani don't go to the starting material again. This reaction here is easy, but it will be easily desulfonated. It will be go back again to the starting material. This easy reaction and reversible, and this is slow reaction but not reversible. This is the difference between of them at high temperature. At high temperature. So why is beta isomer is more stable? And the alpha isomer, the large SO3H group, Sprenius silver streak handle here, because it is near from the this area here. Okay, so it will be especially crowding steric effect because it's pumped into the hydrogen atom located on the adjacent ring. Okay, at 8 position. This here alpha position, when the SO3 come to here like this, SO3H come to here, we have here a steric handled with the hydrogen in this position. Okay, in this position. So when SO3H near from this area here, it will be have steric effect or steric handle with this hydrogen position here. But when the SO3 at beta position, it is so far from the hydrogen point here. For this reason, it will be more stable compound, more stable product. This more stable than this, more stable than this. Here it is very clear for you. Here we have repulsion, okay, steric handle, and here we don't have repulsion, or the repulsion is so little here. So this is more stable than this. For this reason, in the high temperature, the more stable product, it will be formed. It will be formed. It will be formed. So at normal condition, normal heating, form the product that is easiest, fastest to form. Okay, is the alpha position. At high temperature, the product it will be formed, it will be the most stable one. It will be the most stable one. That meaning is the beta position. Beta position. So here the halogenation again, non-catalyst required for the halogenation. Also in halogenation, special bromination of naphthalene, which is a classical example of an electrophilic aromatic substitution reaction. Normally here, if you want to add bromine to standard benzene, you have to use strong Lewis acid catalyst. You know the normal bromination in electrophilic aromatic substitution, we need catalyst like FeBr3 or AlBr3 to make bromine electrophilic enough to react. Here in naphthalene, however, it will be more reactive than benzene. Naphthalene is more reactive than the benzene. So in this case, we don't need catalyst here toward electrophilic aromatic substitution benzene, because the electron cloud is more readily available to attack for the electrophile. That meaning in naphthalene, here in naphthalene, one of the aromatic cycle, it will be activate the first or the second aromatic cycle. Okay, so in naphthalene, both the aromatic cycle, they are activated and highly electron density here, so it will be react with the bromine without Lewis catalyst. We don't need Lewis catalyst here. Okay, we don't hear Lewis catalyst. So the problem with the for example, with the Friedcraft alkylation of naphthalene, because it is active cycle here, active cycle, both of them, the active cycle, the polyalkylation, it will be happened for the naphthalene. Polyalkylation, not just one alkylation, it will be happened polyalkylation. A classic problem in organic synthesis for polyalkylation during Friedcraft reaction of the naphthalene. Why does the polyalkylation it will be happened? Here to understand why naphthalene ends up with multiple alkyl group, we have to look at how first group change the chemistry of the molecule. How the first group it will be change the stability, it will be change the energy of the molecules. Inshallah, this we will talk about it in the next lecture, lecture number 3. I will stop here and thank you for listening. See you later.